Hello, my name is Michael Ventura, and this is my um, experiment for the Lab 2 magnetic field of a bar magnet. So let's get started with the introduction. Okay, so the main goal of this experiment is to calculate, or the main goals of this experiment is to calculate the magnetic dipole moment of a small bar magnet. And in addition to this, we were also trying to discover the distance dependence of the magnetic field due to the bar magnet. And we're also trying to compare this dependence to an off-axis formula and measure the magnetic field of a bar magnet and account for the Earth's magnetic field, which is really important. And so the results are shown below. These results are very wrong, as I did some errors in the experiment, and these will be addressed later. And yeah, I will continue on to some physics principles that are really, really, really important to understand when trying to understand like what is going on in the experiment. And so the first one is Biot-Savart law, and he describes the magnetic field due to a constant electric current. And this equation below, or like on the slide, is shown, and we use this equation to really create values out of this experiment. And then the magnetic dipole interactions, which state that bar magnets have a north and south pole, which creates a unique electric field, sort of like a dipole. And magnetic dipole moment is a vector quantity that describes the magnet properties of the magnet. All right, so in this experiment, we're using the Telemeter app to determine the magnetic field of the magnet. And there's two really main points with this, and we need to account for the Earth's magnetic north by making it x equals 0. And so this is actually really important, as it will like allow us to correct our calculations later. We also found where the magnetometer chip was in the phone. And to do this, you kind of just move your phone and the magnet around and see how it works. Then find the distance dependence of the magnet. And so we have to find the values of R, where Bx is equal to 20, 70, 120, 170, and 220. And so in order to do that, or the reason we do that is to get a graph and like have like a nice linear kind of showing, and so like they're evenly spaced out and such. Then we compute the averages for the 3 trial runs. And then we plot ln bx versus ln r to get the equation shown. And in that equation, n is equal to the distance dependent. And then after that, we use the formula to we use the formula above and the magnetic dipole on axis formula to calculate the value of mu. So these are my results of the experiment. On the top right corner, you can see my GlowScript code, and this GlowScript code kind of just shows like basically just like what a dipole is, and it shows the magnetic field of a dipole, and then the pink is the net magnetic field. And then to the side we have my graph, which is obviously wrong. The y-intercept should be larger, and that's the same with the slope, or I guess it should be more negative. So like numbers such as -5 and -6 should have been seen. As you can see, mine were very small, and yeah. All right, so some what ifs. The first what if is, if the magnetic north was not oriented before we could use the readings, so the magnetic north was not oriented before we could use the readings that the app provides as a value before starting, and this only means that after we would have to correct for those values. And then what if if two magnets were used, then the dipole moment would double, and this would then mean that the measurements would differ by a factor of 2. And that concludes my presentation. If you all have any questions, feel free to message me, and that'll be all. Thank you.